Next we have David Dillow and Huang. They're going to talk about LNet routing enhancements and extracting maximum performance. Isaac is from Xyratex, and Dave Dillow is from Oak Ridge National Laboratory.
So this is next.
Yeah, forward, backward.
Okay.
This is the shock collar if they don't applaud.
Okay.
Next we have David Dillow and Huang. They're going to talk about LNet routing enhancements and extracting maximum performance. Isaac is from Xyratex, and Dave Dillow is from Oak Ridge National Laboratory.
So this is next.
Yeah, forward, backward.
Okay.
This is the shock collar if they don't applaud.
Okay. So in today's presentation has two parts. In the first part, I'm going to present the routing enhancements we've done at Oak Ridge to get better throughput and reliability out of our routing system. And the features I'm going to talk about includes the router shuffler, which is a very simple change, but that yields surprisingly better load balancing among the routers. And the next one would be the asymmetric router pinner, which is basically a smarter router pinner that could detect and avoid router failures asymmetrically. The last one is the fine-grained routing that makes it possible to exploit locality in the network to get better throughput. And next, Dave is going to talk about how to use multiple LNets to extract maximum performance out of a complex network. So first of all, the router shuffler. So in the past, we initialize each client and server with the same set of routers in the same order because we thought that the order of the routers would become randomized over the time very quickly, because after each use, the router is moved to the end of the list by client and server. So that overall we would get balanced load among the routers. We had believed so for a very long time until Sandia sent us these pictures. Basically, these pictures were gathered during two write tests. From the top one is from 2,000 clients and the bottom one from 6,000 clients. So the x-axis shows the ports on the switches. Number 1 to number 50 were the router ports, and the y-axis was the time, 0 from the top, and it goes down. So the load received on each of the ports were color-coded. So blue means there's no traffic, and green means some traffic. So this graph immediately told us three things. The first thing is that there are very noticeable blue stripes, blue gaps in the graphs, which told us that during any point in the time, the 2,000 clients were only using half of the routers available, and the rest of the routers stayed completely idle, which is very bad. But the good news is that there is very little variation in the color, so that means at least among those routers in use, the load is distributed fairly evenly. And the bottom graph were from 6K clients, and which showed roughly the same pattern in traffic distribution. So the fix were rather simple. So instead of hoping that the order of routers would become randomized over time, we explicitly initialize the router set in a randomized order during startup. So, and in the end, we've observed, like in a test, we've observed a 10% increase in aggregated throughput in a test. But unfortunately, I couldn't locate the same graph after the patch was implemented. So the next one is the router pinner. We should go to the, so in the picture here, there are two client clusters connected to the same server cluster by routers, and clients would ping the routers so that if the router fails, the router would be avoided. But there's a problem with that approach. For example, if a router in the TCP, in the Ethernet cluster has a bad cable, the clients in that cluster would be able to detect that failure because the router would stop responding to pings from the client. However, since the router's interface in the InfiniBand server network is still good, so the same router is still able to respond to pings from servers. So it's highly likely that the request from the client could reach the server without any problem, but the service reply could be forwarded to a router that has a bad Ethernet interface, because the router could still respond to pings from the servers. So in the end, the reply would never reach the client. So the solution we had implemented was to simply make use of the ping replies from routers. Instead of sending a meaningless reply back to the clients and servers, we include in the response a list of the interfaces status on the routers, so that the clients and servers would have a complete knowledge about the health status on the routers. And in the example I just gave, the servers would now be able to avoid the router with a bad interface in the Ethernet network, because it knows from the response from the router that the router has a bad interface in the Ethernet. And the next one is the weight routing. So in the picture here, all the routers to the server network or to the client network are treated the same way. So clients and servers will try to distribute the load evenly among the available routers. But the problem with that is in a larger network, it's often impossible to connect the routers to the servers on the same switch. So in other words, some routers will be closer to the servers and some would be further away, and the path between the routers and the servers would involve inter-switch links. In the test we perform at Oak Ridge, we have observed like a 15% increase in throughput if we were very carefully choosing which routers to use to reach the servers. And so the solution we had is fairly simple. So instead of treating all the routers the same, we divided them into groups and assigning a different way to different groups. So the routers would try to avoid those the clients and servers would try to avoid routers with a higher weight, unless there is no lower weight router available. So the configuration would look like this. It's very simple. So the mechanism itself is fairly simple and straightforward. The much more difficult problem is to find a routing policy that can make use of locality in a very complex network, and at the same time take into consideration problems like administration overhead and high availability, which is what Dave is going to talk about.
Alrighty, let's see here. So, what is fine-grained routing? To build on what Isaac was talking about, it's basically we're going to use LNets to control the network flows. I only have about 15 minutes at this point. Isaac, you went really fast. So I'm not actually going to be able to go through all the details that we've worked on from this. There's a number of papers that the team at Oak Ridge has put together, and these will be in the slides online, so you don't have to write down the URLs now. But why do we really need to control these network flows? Well, at the scales we're running at now, congestion is a real problem. As you can see here, as we sit up and we get up towards 96 OSSs on this system, and this is it's Jaguar, it's 18,688 compute nodes talking to 96 OSSs at this point. This was all actually directly attached. We're not even doing routing at this point, but even on that really good network there, we're still losing about 30% at the top end, already just off the top. And it doesn't stop there. InfiniBand is very similar. We're even losing more on InfiniBand than we were losing on the C-Star Taurus. If you sit there and you inject, it's mostly a fat tree. If you sit there and you inject from the wrong place, you start to congest on the internal network. You start getting head-of-line blocking, so that even traffic that's not trying to use the same link starts getting backed up a little bit farther in. So this is a real problem, kind of drives us to want to control that. So how does LNet contribute to this problem? Well, LNet routing gives you the worst of both worlds. You've got every message that goes to an LNet router or from a client, every time it wants to talk to a particular network on the other side, each message goes to a different router. So if you've got 8 different routers, 8 messages are going to go through 8 corners of your network. And so that makes it really hard to predict where your traffic's going. And if you can't predict where your traffic's going, then you can't have your applications or your middleware sit down and take advantage of that and say, hey, I know that I'm here in the topology, and I actually want to be talking to this OSS over here. Maybe I don't want rank 1 to talk to that. Maybe rank 10 is closer, and I should have him do that I/O. So that's one way of avoiding the some of the bottlenecks that we see in the Taurus and also in the InfiniBand network. But because we're sitting there, we're throwing packets all over the network willy-nilly, we can't really tell where we're going. So our approach was, let's use multiple LNets to pull this in. This allows us to steer the traffic. We can be very selective about where we're sending things. But there's a couple of different ways we can go about doing this. We can sit there, we can have one LNet per IB leaf switch. So in a factory, you build up a network out of multiple leaf switches. In this case, we're doing DDR, so it's 6 routers, 6 OSSs on the 12 ports pointing out. So we want to be able to stay within that crossbar, so we don't actually go traverse the fabric at all. So if you're doing that, you can sit there and say, well, I'll use my clients with nearest neighbor, and I'll assign them an LNet to use to talk to those OSSs based on where they are in the Taurus. Well, that works out pretty well, but then if you want to actually place your I/O, it complicates your calculations for that. Plus, your I/O that you can actually get out of the system becomes very dependent on your job size. The larger your job, the more routers you can actually use, because there's only 32 groups. So if you're a fairly small job, you're only going to be able to use 32 routers. If you're a really big job, you can use 192, and you want to be big for that. We also look at using round robin. In this case, instead of saying, well, we'll just use the nearest neighbor, we'll still throw our network all over, or our traffic all over the network. But now we have a very predictable pattern based on what our node ID is, so that we can always sit there and say, well, I know exactly which router I'm going to talk to from here. It's very predictable, but now we're throwing traffic all over the place, whereas with nearest neighbor, maybe we're not stepping on the other guys using the machine at the time. Round robin, we're still throwing traffic everywhere. We're stepping on everybody else. So we also tried a different approach, which is, hey, let's just do one LNet per OSS. And this lets us sit there and say, now we've got 192 O2IB networks. I always know which router I'm going to talk to a particular OSS. I've got 192 routers, 192 OSSs. This matches up really well. And what we just call it is a projected routing. We basically said, we're going to pretend these routers actually live in the Taurus itself, and that makes everything really easy. It's easy to think about. So just kind of a graphical we can talk about. So in basic routing, ignoring the projected routing here, but in basic routing, any one of these clients, when they start talking, they're first going to talk through the red router, then they're going to talk through the blue router, then the orange router, then the green router, or some other randomness, or other random setup as Isaac had talked about. And then with nearest neighbor, then everybody right around the red router, right around the blue, are going to sit there and use those set of routers to go to the 2 different IB leaf switches that are the rectangular pieces up there. But for projected routing here, we're always going to use the green router to talk to the green OSS. Always going to use the red router to go to the red OSS. This way traffic always stays on that crossbar, and we're good. We also still have a fabric out there, so if we have other machines, like Spider is a center-wide file system, so we really want to have, we need to have access to all these OSSs and from everybody. We can't just go out and say, well, it's only going to be talked to from the Jaguar machine. So we still have that, but we can avoid crossing it for the bulk of our I/O. So what does this kind of look like when you're configuring things? And I wouldn't recommend using this exactly, because I actually typoed a couple of things in here as we went. The top one says OSS1, and so we've got 192 different configurations like this. The big changes are highlighted in red. So O2IB 201 for OSS1. The bottom one is supposed to say O2IB 202. So once again, don't use this. But as you can see, the routes change for those. Now portal 1 is Jaguar. Portal 0 was Jaguar XT4, or become baby Jaguar at one point, as baby as an 8,000 node machine can be. But you can see what we're sitting there using 3 different routes to get there. And we used the weighted routing that Isaac added to LNet to be able to say, well, normally we want to go to this 1036.229.1. That .1 router is our primary router for this OSS. But if he fails, well, we need to still be able to get to that router, or that OSS. So now we'll use the .97 router. It turns out .97 actually lives on the same blade in the Cray, but That's okay. We also added a third one just in case that blade fails, and it goes into a different IB switch altogether. Now we're going across the fabric, but hey, we can still talk, so we're good. The .7 router. And you can see it kind of just, every OSS has a very similar configuration. We picked 3 routers for it. We kind of go, and how you pick those IP addresses, how you pick which routers you're going to use, that's going to depend on your topology, and there's more information about that in the paper. The router configuration is dead simple. For each router, he's got to be primary for the Jaguar side, for the portals network on C-Star. He's got to have O2IB0. He doesn't actually have to have that, but it's just kind of nice to have. The clients don't know about that, so they'll never use it. But he's got to have all the O2IB LNets that he's actually going to talk to. So in this case, at router.1, he's primary on 201. He's the second backup for O2IB 202. And he's the third layer backup is for O2IB 208. Similar for 97 and for 7. You can see I've got the NIDs there, which will be more important later, just to kind of have to figure out how the clients are going to find these. So the clients are finding these. One of the big problems, we got 192 OSSs, we got 192 routes to add. You can't fit that in 1 kilobyte, which is the maximum length of a string on the module parameters. So you can't actually add the routing configuration for modprobe.conf like you do normally. And frankly, I don't want to sit there and manage 192 different modprobe.confs. Fortunately, I don't have to. Jason and Dustin and everybody get to do that. But I don't want my sysadmins too mad at me. I mean, you got to deal with me enough anyways. So what we did, we put in a large configuration file that just said, to get to this net, we're going to go with, here's the NID you need to get to. And then we read that in from a file. When we run a script, as soon as we mod probe LNet, we bring it up on the clients, and then we cat this map in, we read it. For each one, we actually do it, just translate it to an lcutl add route. And so this becomes really nice. Everybody gets the same config file. Everybody gets the same script, and it's really nice and easy to run with. We use a similar thing to actually generate the network for the routers, and we do the same thing to generate the configurations for all of the OSSs, so that, hey, we don't want to maintain multiple files if we can help it. And so, what's the end result of all this? Well, as it turns out, we actually get some pretty good performance out of it. We had some applications that got up to a 30% reduction in their runtime. And that's really huge when you consider that these guys were actual real application runs. They were all running at the same time. And we weren't sitting there just saying, hey, applications aren't just going to sit there and do I/O. Much as us lesser guys would love that to be happening, because, hey, then we're really important. We are important, but boy, we really have something to show for it. That hero number would really mean something maybe. But getting an actual 30% reduction in runtime just by changing your routing configuration on a real application, that's kind of a nice situation. And you can see we did a little bit of measurement between the different configurations we had. And some of those, the second from the left there is S3D, really hated the nearest neighbor. And part of that became, it actually ended up being, this is the highlight of if I sit there and do nearest neighbor small jobs, and the S3D jobs weren't really that big, they kept getting shoved into a corner of the machine, and they were only using 32 routers. We took any other configuration, they were able to actually take advantage of all 192 routers and actually get a performance boost. And so with that, we have a few minutes left. I actually did fly through that. Are there any questions?
Hello?
There we are.
It seems like you've taken over the hop count argument to the routers. Is that going to conflict with, you're using it for a wait now, it looks like.
So the wait I'm not actually using. So routers, LNet will sit there and use all the routers in a given weight class. So if you have a weight class 1 with 3 routers in it, as long as one of those routers is up, it will never use anything in weight class 11. So it's only those 3 routers that are actually being used. The weights are only really good for falling back of say, I want you to really use these over here, but if those are all dead, go to the second class. Does that make sense? And so we use hop count to determine placement for nearest neighbor or for doing optimizations on those things. But hop count doesn't really change too much for, doesn't really come into play too much for the different setups. I think I've answered your question, but
Well, it just seems like it would conflict with other people configuring with hop count.
So So you mean everybody else configuring with how I put my router, where I want my routers based on hop count?
No, but the way you did it, you
Mhm.
used the hop count variable for weights, it seems.
Yes, absolutely.
Okay.
Which when you look at it, for most of the network routing, the weight piece comes from what people have been doing in IP for a long time for static routes, which is, hey, what's my weight? Well, they use hop count for that weight because in IP space, farther away is worse. And same for us with HPC, farther away is actually worse, but not quite as bad as it is when you're going over a WAN. So instead of putting an actual hop count in there, I'm synthetically making one, yes.
Okay.
Dave, you spoke some about how this impacts performance, and we see that congestion is decreased and you can improve application performance. Can you comment on, are there any impacts to total cost when you're deploying a large-scale global file system?
Absolutely. If you can take advantage of this and you localize all your I/O, you don't necessarily have to buy a big core switch to fit all of your stuff into one switch. You can end up buying a number of one-use switches because you really need to worry about keeping everything on that crossbar. And if you've got low I/O demands going off of that switch, like if you're not running a center-wide file system where everybody needs to get 1 terabyte a second, maybe some of your guys only need to get a couple of gigabytes a second. Well, you don't need 12 links coming off of that switch to go in somewhere else. You could use 4, and that would be plenty to get you where you want to go. And so that really helps out that quite a bit. It just really depends on what you want. I mean, you don't have a lot of traffic between OSTs and MDSs, so you don't need quite as much bandwidth between those. So you can allocate your links better. And I should point out, I think Cray will end up talking about this because I know they're doing some work in this space. And as I point out, LNet or the fine-grained routing isn't limited to LNet routing. NASA's doing some really interesting work in this space where they're using multiple LNets, multiple IB adapters on the same node, and being able to take those and increase the per client bandwidth just by splitting their traffic across both the LNets and the IBs available to them. All right.
Right. Dave Dillow.
Thank you, guys.